In today's video, we're going to look at electromagnetism, which is the phenomenon whereby electric currents produce their own magnetic fields. And we'll see how this works in ordinary wires, coils, solenoids, and electromagnets. Let's start by imagining that we had a wire, and that we let current flow through it from bottom to top. This electric current would produce its own magnetic field all around the wire, which we can represent with field lines. In this case, the field lines would be concentric circles around the wire, and they'd be closest together near to the wire, as that's where the magnetic field is strongest. The direction of the magnetic field, though, is going to depend on the direction of the current. So to help us remember which way it goes, we can use something called the right-hand rule. If you take your right hand, curl it into a fist, and point your thumb in the direction that the current's flowing, then the direction that your fingers are curling in tells you the direction of the magnetic field. So for our wire, in which the current is going upwards, the magnetic field would be going anti-clockwise. And so we would mark each of our concentric circles with little arrows in that direction. However, if we had another wire, with the current going in the opposite direction, then by using the right-hand rule again, with our hand upside down this time, we'd see that the magnetic field is now travelling in the opposite direction. To make things a bit trickier, let's now imagine that instead of two separate straight wires, we instead joined them together, so that we had a single flat circular coil, with the current flowing in through the bottom left and out through the right. As the magnetic fields of the two sides of our coil interact, the magnetic fields, which were concentric circles, will now get stretched out and form ellipses. And as the magnetic fields combine, they'll form a single magnetic field which runs straight through the center of the coil, which, if we were to look at it from above, would look like this. If we now add lots more turns to our coil, all next to each other in one long piece of wire, we make something called a solenoid. And importantly, the magnetic field within a solenoid is strong and uniform. Outside the coil, the field is just like the one we'd find around a bar magnet. And just like a bar magnet, where the field lines come out is the North Pole, and where they point in is the South Pole. So we've effectively used electricity to create a magnet, and so we call it an electromagnet. One of the useful things about electromagnets is that they're only magnetic for as long as we keep the current flowing through the wire. As soon as we turn off the power source, the magnetic field disappears, and when we turn it back on, it comes back. As well as being able to turn it on and off, we can also reverse the direction of the magnetic field by reversing the direction in which our current is flowing. We can show this by reversing the direction of our little current arrows. And each time we flip them, the direction of our field lines and the sides of the poles will also flip around, indicating that our magnetic field has flipped directions. Now, the problem with our electromagnets here is that a small electromagnet like this one would only produce a very weak magnetic field. So you need to know the 4 ways that we can increase an electromagnet's strength. The most obvious way is just to increase the current that flows through the solenoid. Second, we can increase the number of turns in our coil while keeping the length of the solenoid the same. And similarly, we could decrease the length of the coil while keeping the number of turns the same. Basically, solenoids that have very densely packed coils will be the strongest. The last thing we can do is add an iron core to the inside of our solenoid. As iron is a soft magnetic material, it will become an induced magnet when the solenoid is switched on, which will massively increase the strength of the electromagnet's magnetic field. But importantly, it will also lose its magnetic field as soon as the current is turned off.